Hello, everyone. My name is Sam Perry, and for my 591 Machine Learning and Optimal Control class, I'm going to be going through and visiting my final project and everything that I did in my study. My study title is Deep Q Learning for Lunar Lander using PyTorch and OpenAI Gym. And so to start off, I'd like to give a brief overview of what we'll be talking about in this presentation. So first, I'm going to be giving an introduction to the content and the subject of reinforcement learning and other related topics. Next, I will be going into the experimental environment in which the study took place and where it was conducted, going over the basics of Lunar Lander and everything else like that. That will be followed up with some related work to the topic that is going to be covered in the study, and then some methods of the study, or where I really dissect everything that the study covers and what everything I did in the study. Um, and then I'll move into the implementation and the results of the study that I've conducted, and then finally we'll move into the conclusion section. So to begin, let's start with an introduction. So reinforcement learning has been widely used approach to solve many problems that possess well-defined environments and other instances. It allows researchers to create policies and agents with little to no available expert data. Um, and when data is very small, typical machine learning methods and models may not perform very well or generalize very well for but reinforcement can really take over because it has the ability to learn through trial and error, using the feedback from the environment to guide the learning. One key topic in reinforcement learning is this trade-off between exploration and exploitation. Um, so exploration is really just covering all the ground, searching every part of an environment, searching every action space. And then exploitation is using the current policy and always picking the best and most suited action for a specific environment based on the current policy that you have. So reinforcement learning has a wide usage in video games, which is one of the topics that I cover which is the topic that I cover in the study. Because these environments are already predefined, and it makes it really easy to define a reinforcement learning problem because you typically have score, you typically have things that can be calculated and observed very easily. And so for this study, I'm going to use OpenAI Gym, which is a pre-built environment library where it has rewards, it has pre-built environments, and things like that. So next, so let's talk about environment. Um, again, I'm going to be using OpenAI Gym. This is traditionally very useful for reinforcement learning research. That is the reason it was built. Again, it has many pre-built environments installed, and the environment that I'm going to be using is the Lunar Lander from the Box 2D library. On the right, you can see the general setup from running it on my local machine. Um, it is very well equipped. It has a large package and it has a lot of different features that can be used with it. So how Lunar Lander works and how it works in OpenAI Gym. So every episode or every time you play the game, the lander is going to start at the top center, so right in the middle, and then it will experience a randomly generated force that sort of sends it in a different direction with different physics and different dynamics. There's three ways to end an episode. The lander either has crashed, where it has made contact with the moon and not landed successfully. The lander leaves the screen either in the X direction or Y direction. This is bad because we can't really track it, and it sort of has veered off course. And then the lander object falls asleep. When the lander object falls asleep, it just means that it has landed in OpenAI or in the OpenAI Gym environment. When an object has fallen asleep, it is no longer colliding with other objects, and therefore um, it's sort of dead. So the action space for the lunar lander environment is four discrete actions represented by integers 0, 1, 2, 3, 4. And those are the actions that you can take as a user or as an agent. Uh, so the four actions are do nothing, fire the left engine, fire the right engine, and then fire the main engine. The left engine obviously controls left orientation, right engine, right orientation. And the main engine is the one that boosts the lander up or whatever direction the lander is currently facing. The observation space of the environment is an eight-dimensional vector, and that's how it is reported in the code. So the eight points of the eight-dimensional vector are the x coordinate and the y coordinate, the x and the y linear velocity, so how fast they're going, the angle, but this angle is taken with relation to the starting center of the starting angle that the lander is taken. So it's straight up. The angular velocity, how fast it is moving in regards to that, how fast the angle is changing in regards to that initial angle. And then two leg booleans, which represent contact with the ground. So each leg has a boolean that a true false variable that um, references is it in contact with the ground or not. And that's what the booleans sort of represent. Uh, the reward function is also defined by the OpenAI environment. Um, it's defined by the objective of the game and the environment that is originally created for this use. As the agent sort of explores this environment, it learns the reward from the states and the sampling from the episodes. So it consists, in the lunar lander sense, it consists of both penalties and rewards, which is very common in reinforcement learning. So the penalties are defined as moving away from the center. This is dynamic based on how far away from the center you are. If you remember from the last previous photo of the lunar lander environment, the landing pad is always defined in the middle of the environment. So moving away from the center is bad because you're not going to be landing in the correct spot. So moving away from the center based on how far you are, that you will get a negative penalty. Minus 100 for crashing, you receive a negative 100 reward for crashing for the episode. And then for every frame, the lunar lander, the sampling rate is every frame that the lunar lander environment runs at. So every frame, there's a minus 0.03 reward for running any of the three engines. So running the left engine, minus 0.03, right engine, main engine. Every frame that is running, you'll receive a negative reward for that as well. The positive rewards for the lunar lander environment are obviously we have the leg booleans, so plus 10 for each leg correctly contacting ground, making contact with the ground. Then you have plus 100 for landing successfully just anywhere on the face of the moon. And then, of course, plus 200 for landing correctly and on the main pad, which is the objective of the game. So pretty large rewards for those to sort of reward the agent for doing the correct actions. So now let's talk about some related work to the lunar landing and more specifically related to my study. So the first paper I looked at was this hands-on intelligent agents with OpenAI Gym. Um, this was sort of a baseline for reinforcement learning in PyTorch and how to implement it. Coming in, I had no PyTorch experience and I really wanted to learn some. So this is a very valuable resource for me. Specifically, they covered deep Q networks in PyTorch and using OpenAI Gym. And this is the approach that I wanted to use for my model, as I talk about later. And so this is a very helpful resource. Another paper that I read was extending the OpenAI Gym for robotics. What this paper did, they created ROS-compatible extension for OpenAI. ROS is a robot operating system. It is a very commonly used robotics code. So this allows robotics researchers to create replicable environments for testing reinforcement learning in robotics. But they can also do this in OpenAI. This is the environment that they allowed to use. And what this paper did was it tested Q networks and SARSA, expected SARSA, using ROS and the OpenAI Gym. And it sort of provides a baseline for robotics researchers to sort of compare algorithms and compare reinforcement learning algorithms with each other in OpenAI Gym. And then the last one I covered was really interesting paper. It covers more of the future of reinforcement learning. Um, this paper is called Unentangled Quantum Reinforcement Learning Agents in OpenAI Gym. Again, this is the future of reinforcement learning called quantum reinforcement learning. And this paper is very significant because it was very recent and it was the first successful quantum agent, which uses quantum reinforcement learning. First successful implementation on IBM quantum machines, which is a large move in the right direction for developing quantum reinforcement learning, which takes advantage of the new advances in computational complexity with quantum computing. And it uses OpenAI Gym and more specifically uses Lunar Lander, the same environment that I was using, to implement this quantum agent. So I thought it was a really cool sort of higher level reinforcement learning agent that on additional on my topic. So now we're going to get into more the meat of my paper, the method section of my paper. So the method that I chose to use was Q-learning. So Q-learning is a temporal difference algorithm defined by that equation on the right. So you have the action valued function, which is the Q function, where it takes state action pairs and it sort of gives a value for them. Um, and it updates these values based on the reward the next state that it's going to get, um, multiplied by this factor that um, sort of determines how well it learns. And then Q learning is also a combination, or temporal difference learning is a combination of Monte Carlo and dynamic programming. So it sort of gets the best of both of these. It gets the complexity of um, dynamic programming or Monte Carlo without having to do all the large memory management that Monte Carlo comes with. So to extend this to deep learning, I used the deep Q learning approach, which basically instead of approximating these um, action value functions through just Monte Carlo sampling or any type of other episodic sampling, you use a deep Q network to approximate these action value functions. You have a policy network and a target network, and they approximate the value functions that you would be getting from the original Q learning approach. And so use this deep Q learning policy network to maximize the rewards from the environment. The reason I used deep Q learning was because in a lot of papers I was reading, or a lot of papers I was reading, it was an extremely popular method that was used, and it was um, one of the more popular methods, I would say. And it's also very quick and accurate for as far as deep learning approaches go. So I decided that deep Q learning would be one of the best approaches to take for the lander problem. So for my model architecture, uh, it's it's pictured here. I use two neural networks with the same exact architecture. I tested two different model architectures, one with one hidden layer and the second with the second hidden layer. And the second hidden layer was far outperforming the first one where there's only one hidden layer. So I chose the double hidden layer neural network architecture. So as you can see, it has 8 input layer cells. So each one of those represents the 8-dimensional observation or each one of the cells represents one of the 8-dimensional vector observations that we see when we're testing the model. Then we pass that into a fully connected 128 layer or 128 node hidden layer. Then we pass that into another 128 node um, hidden layer. And then finally, we fully connect that to an output layer, which outputs one of the 4 actions that are possible through an integer, 0, 1, 2, 3. And then it allows us to sort of just output the action that we want. And I landed on this architecture through a little bit of testing. Didn't have much time to test because, again, I used the laptop to test this with only 16 gigs of RAM. So I didn't have the most powerful computational power. And I also needed the laptop for other things. So this is the architecture that I settled on. So for training, I settled on 200 epochs, which took around 30 minutes. I thought this was a reasonable training time. 128 batch size. This was kind of standard through a lot of the papers that I've read. This was really quick to perform, and it performed similarly to other batch sizes. I don't think it was the most influential on the performance. Uh, so the learning rate was set to 0.0001. This is also uh, it was a static learning rate, and this is also pretty common in some of the papers that I read. Other papers have done a dynamic learning rate where it's larger at the beginning and smaller at the end, so it sort of learns in bigger steps. But I thought this would be fine enough for the model that we're using. I used the PyTorch's smooth L1 loss, which is similar to a Huber loss, except it performs a little bit better and sometimes will handle some disappearing gradient problems that could happen. So I figured that the smooth L1 loss would be much better for this um, for this simulation. As you can see on the right, this is just a video of the model training. It's running into some issues with some hovering, so this gets fixed later on in training. And then I also use the Atom optimizer for gradient descent. Atom is a very, very popular optimizer created a while ago. but it uses gradient descent to sort of optimize the model. And I figured that it's one of the most popular. This is a semi-simple problem. I figured it should be perfect for it, and there would be a lot of resources to help me learn more about how to use the atom optimizer in PyTorch. So for training, we there was data sampled and stored from the environment. So every episode you saw, it was recording that data and sampling it with different actions using the policy network. The policy network actually was trained on some math data. So instead of the entire episode, it did not get the final state, so it didn't know the final reward. So it would predict this value without the final reward. And then the target net trained on the unmasked data, where it did receive the final reward to sort of get the value function for the entirety of it. Um, for the target net, I used this thing called soft target net updates, which comes from a paper that is in my resources, um, where it says that the soft target update allows the network to more slowly converge, and it helps relieve some of the update divergence that can happen. Because if you think about it, you're updating your target net based on the policy net. If you do that every time, um, you're not really getting a settled target net. So what you do is you sort of update it every now and it doesn't move as drastically, and then you can sort of move it towards that more golden equation that you're looking for. And you do this by setting um, a tau. A tau in the paper was set to 0.001, which basically just references how often you are going to be changing up the parameters for the target net in regards to and changing the policy net as well. The policy net is not on the soft net update, so the policy net will be changing every time, and the target net won't be. Again, we're going to talk about this key idea in reinforcement learning, exploration versus exploitation, which is like how often do you follow the policy and how often do you do other things? How often do you stray from that policy? So what I did in this paper was I used a decaying exploration rate. Um, so what this means is it starts relatively high, and then as the model learns the environment and sort of learns how to exploit the environment, it decays more rapidly. Um, so it goes from 90% in the beginning where it's making basically completely random actions, and it decays to only 5% over the training. So the model has learned like better. Even once the model has fully converged, it is still around 5%, which allows for some exploration. And I thought this was pretty standard for some of the reinforcement learning papers, which is why I included and opted to use the decaying exploration rate rather than either a 25%, 75% split that is pretty optimal. So that's why I did that. So for the implementation and result section, basically I rated performance based on the highest rewards gained and plotted our rewards versus epoch graph. And I also wanted to complete this with speed because of the computational power. So the faster I can get it done, the better. I kept the 200 epoch standard because I figured that this would be the model performed well enough with the 200 epoch. It could definitely use more training, but I just didn't have the computational power or the time to do that. So some of the issues I ran into, again, I was using my personal laptop, so didn't have the most computational power, and it was in use a lot of the time. Uh, Setting up OpenAI environment, I had quite a bit of trouble with that. I ran into some licensing issues running some of the Pong examples, so I had to manually install the library and get all the dependencies ready. And then also you see that hovering issue during the training. That was fixed through some model tweaks and hyperparameter tweaking that is in the final model. So there's that. So this is the one layer model. As you can see, it's just super bouncy. Between episodes, there's not really a consistent convergence. The blue line is the reward every single episode, and the orange line is the reward over a moving average of 100 episodes. You can see that it has not converged yet, and over more training, it possibly will. But it's still super bouncy. It doesn't really converge. You can see that it's sort of exploring in the middle where it goes down and then pops right back up with some more optimal solutions. The moving average is still increasing, meaning it still has some more training to do. But again, this is not the final model. The final model that I chose to use is the 2-layer model. And as you can see, it learns much quicker than the 1-layer model. And it also converges a little bit nicer than the 1-layer model. As you can see on the around episode 25, it reaches the same performance that the original or that the 1-layer model did at the beginning. Again, there's still fluctuations. So around episode 75 to 125, it's kind of converging, and then it sort of explodes rapidly. Um, this is due to either some hyperparameter tuning that needs to be done, and then also some more training that needs to be done. Uh, if we see the moving average, it's kind of tailoring off, so it can see to be converging. This can still converge a little bit more and sort of land at the optimal solution. But as far as visually, it looks very good when the lunar lander agent is actually playing. So for the conclusion, it actually surprised me how quickly the last model improved and how it was past my expectations, really. Visually, it's a very, very good lunar lander player, which I was not expecting from a pretty simple model and with very few training time. Um, Again, a deep Q learning is probably a great policy approximator for this specific problem. I think it worked very well. There's still some convergence issues that I think in the future this can um, be solved through some more hyperparameter tuning and longer training sessions, which is interesting to look out for. So the future plans for this project obviously test other methods and then using deep Q networks for other games. Also, maybe fixing some of those convergence issues that stumbled upon that where it didn't really converge to an optimal solution even towards the end of training. Um, and then for as far as just my future plans go, I'm going to apply this reinforcement learning in my career, sort of changing problems to a reinforcement learning problem, so it can be much easier to solve and sort of better for the um, tailored to the environment. But with that, I hope you learned something and you enjoyed my presentation. Thank you.